Okay, today we are going to discuss about another machine learning related algorithm. Not one, but a class of algorithms, uh, basically based on a specific type of learning algorithm known as decision trees. So, decision tree, and then we are going to discuss about the practical application of decision trees in machine learning, which are based on a technique known as ensemble methods. So pure decision trees are not generally used in practice in today's world. Mainly that ensemble method. So that means a set collection of decision trees are used instead of using a single decision tree in practical applications of decision trees in machine learning. So decision trees are not something new. I think most of you have heard about or seen decision trees in uh, your existing knowledge, right? Basically, it is something very simple, right? So you might have learned these things in your high school. So we'll show you what a decision tree is, and then you can see what is a decision tree. Right? So this is a bit not before learning about the machine learning application. Just see what is a decision tree. For example, in this case, I have taken the cardiovascular disease predictor. Right? This is a classifier, of course. That means based on certain variables, age, BMI, and some other, uh, and mainly these two, right? Age and body mass index. Uh, we can do some classifications uh, for predicting a person's the person's healthiness, or whether he is diseased, whether he has the disease of cardiovascular disease, or whether he is healthy, right? So these are the two variables that we are using here, which is the age, whether the age is greater than 35, and the body mass index is greater than 80. Using these two variables, we can make a decision tree, which is a very simple decision tree, as you can guys can see, where you can add some data points into the decision tree and classify whether that particular person is healthy, or whether he has cardiovascular disease. So in this case, you can see there are two main variables we have used. One is both of them are actually categorical variables, right? So age is, whether the age is greater than 35, it is a binary variable where it has two values, which are true and false. The body mass index, whether it is greater than 80, it has two values, that is two classes, true or false, and so on, right? If age is greater than 0, then we check whether that person is smoking or not. And also we after checking whether the body mass index is greater than 80, then we check whether he's a vegetarian or not, or whether he's exercising or not. So those are also some of the variables that we are using in this decision tree, whether these are age, whether the age is greater than 35, the BMI is greater than 80, whether he's smoking, whether he's a vegetarian, whether he's exercising. With these 5 variables, we have made a decision tree in this example. So I think most of you guys have learned these kind of trees in your schooling days also. This one is generally, this is actually, we call it the tree, but it is, it's an uprooted tree. Uprooted means the root is at the top and the leaf nodes are at the bottom, right? In this case, these are the nodes of the tree. Right? These variables are relevant to the nodes. The topmost node is known as the root node. The bottommost nodes are known as leaf nodes. And the nodes that are inside the tree, which are not root nodes or leaf nodes, are known as internal nodes. Right? And each of the leaf node would be predicting uh, the classes of the outcome classes of the decision tree. In this case, we have selected actually binary variables for all the uh, nodes. So you get only two outcomes from this decision tree, whether he has the disease or whether he is healthy. Right? So this in this uprooted tree structure, you can add some data points into the data structure once you have built this data structure. Sorry, this decision tree, and you can predict whether that person has disease or not. Uh, you can see in each of the variable is a categorical variable, and they are branched into uh, classes of that particular feature. Whether he's smoking, there are two classes: whether he's true, yes, smoking, or false, where he is not smoking. So those are the two classes of this variable, because all of them are categorical variable. In this case, a binary categorical variables. So in each of the prediction, we start with the root node, and we go to each of the branches and end up with the decision or the prediction from the tree. Right? So, so actually, this decision tree is form of a machine learning model. If you can train it, right? That means if you can build a tree like this with the machine learning algorithm or some, yeah, right? Machine learning algorithm is basically a you can say it's a machine learning algorithm because it's a, if you can do some optimization based on the data, and if you can build a tree like this with your available variables, then you can predict with your data uh, for uh, classification problems with the given data set, right? So now let's see how to make a build, how to build the decision tree. In this case, for example, I have taken, let's say you have three categorical variables, binary categorical variables for the simplicity, right? And one dependent variable, which is y. Right? So now we can make decision trees out of these decision variables to predict that particular y variable. So let me show you some different ways, like you can draw a decision tree starting from any x variable as the root variable, right? Uh, and for example, you can start with x1, and then based on, so there are two classes from the outcome of x1, and either you can have x2 here and x3 here, or you can just instead of having x3 here, you come with just return the outcome, and then after x2 you can add x3, or different ways you can uh, make this decision tree, right? So when you add the variables to this model, right? So although you have three independent variables, when you start with a certain variable, uh, you add new variables only if that particular variable can't simply classify your full data set, right? For example, if x1 is the age of the person, right? So if the age can completely classify your data set into two, whether that person would have cardiovascular diseases or not, then you don't have to think about other variables, right? If a single variable can do it, you stop it here, right? So you don't have to add other variables, so you can stop here, right? If not, then you have to think about adding new variables, right? So when you want to add new variables, you have to add new child nodes to the tree where the branches are created, right? So when you can't classify your data set into the classes, that is known as the problem of misclassifications, right? So in this with this categorical variable, if you can't uh, classify your data set correctly, that means there are misclassifications, or your your classification is not pure, right? Classification is not pure means you can't correctly classify your data set with this particular variable. That means there are some impurities. So you add new variables to your uh, decision tree only when there are impurities in this particular node, right? If this node can be 100% pure, or there are no impurities, then you don't have to add any of these new variables, right? So even after you add some variables, uh, you would have want to add another variable or another variable uh, only when there are impurities in those particular nodes as well, right? Otherwise, you don't have to add new nodes. So that is the basis of the decision trees, the decision tree creation. Right? So in this way, you can create uh, different types of decision trees. For example, you can start with x1, and then you can add two decision variables x2 and x3 here. Right? If the x cannot be, x variable is cannot classify it with 100% purity. If there are impurities, you can add the x2 and x3 here, or you can simply add x2 only, and if the other side is okay, right? And you can add x1, x2, x3, and so with a much deeper tree. Or if your data is perfectly explained by, or sufficiently explained by this particular uh, decision variable, then the x1 would be sufficient, right? So there are different trees that you can create with the given data set for the given set of variables. In this case, x1, x2, and x3, right? So when you are creating a decision tree, uh, you have to think about the purity in each of the node, right? Uh, so the idea of the decision tree is to improve the purity of the classification in each of the nodes when the nodes are added to this particular tree, right? So in in the decision tree, you are going to make it with a set of parameters, basically the categorical variables, and each of the new categorical variable is added to the tree in whatever the location, based on the idea of reducing the impurity or improving the purity, right? So it's a problem of optimizing for reducing the impurity or increasing the purity, right? This impurity is also can also be considered as the error in this decision trees, right? So if after your decision tree is making predictions, if there are still some impurities, that means those impurities are relevant to the error, right? So we are trying to create decision trees to minimize the errors of the decision trees, right? So this is the basic idea, right? But when it comes to the variance problem, then you have to think about it again, right? So we will discuss it about this effect. But with decision trees, when you have sufficiently large number of variables, you can have a very highly accurate but maybe a off-fitting model, right? Uh, but however, when you are creating a decision tree, uh, when you are trying to create the optimum decision tree with the given set of variables uh, to reduce the impurity, uh, this becomes a uh, very difficult or computationally highly expensive problem, which is known as a NP-hard problem, right? So NP-hard is a uh, mathematics related classification of problems where you can't simply, when the number of variables are increasing, it's becomes exponentially difficult to uh, solve this problem, right? So we don't have to think about these theories behind these complexities of this problem, but the thing you have to keep in mind is that when the number of variables are increasing, uh, in order to find the best decision tree, that means that the decision tree that can minimize for the impurity to the maximum level is impossible when there are high number of uh, variables, right? Because of that, uh, finding the optimum decision tree for a given set of variables is almost impossible unless the number of variables are very low, right? Because of that, uh, you can't find the because due to this reason you can't find the globally optimum solution uh, for the decision tree problem, where you can't create the optimum decision tree. You can use heuristic techniques, right, to create to find an optimum decision tree, but this particular decision tree may not be the globally optimum decision tree. That means it may not be the optimum decision tree, but it would be a better decision tree among the possible decision trees. But the idea of using the heuristic algorithms is to uh, compute the optimum decision tree within a finite time, right? So you don't have uh, infinite amount of time or infinite amount of computing power. Like you don't have many supercomputers to calculate the decision trees, right? So you have a limited computing power, and you can't wait for months or years to do a calculation. So you have to use a heuristic technique for finding a optimum decision tree, which may not be the globally optimum decision tree, which would be having the minimum amount of impurity, right? So with these heuristic techniques, you can find uh, a, optimum, nearly optimum uh, solution. So there are several techniques like that. There are several heuristic techniques. So CART algorithm is one of the heuristic techniques for finding the uh, optimum solution for decision trees. So now let's see what is the CART algorithm. So the CART is actually stands for classification and regression tree. So this is actually a name of this algorithm where you can use this CART algorithm for both classification and regression. But in when we are learning about this algorithm, we are mainly focusing about the classification problem. So using this algorithm, classification problem, we are explaining about this cart algorithm, but by using the same classification based cart algorithm, you can use it for regression as well. So we will discuss a little bit how it is, how this classification algorithm is used for regression as well. Right? And when it comes to cart algorithm, there are two problems. There are two decisions has to be taken. Right. In this particular algorithm, there are two problems that it is solving at each point. So this is how we are going to understand this algorithm. This first problem is how to select the x variable to get split on each node. Right? So that is simple, right? So how to add the first root node, then how to add a child node. Uh, so what is when we are adding a new child node, what is the next x variable that we have to add? That means when you are adding, so you have a set of uh, categorical variables, so independent variables known as x variables, right? So when you are creating a decision tree, you have to take uh, x variables one or the independent variables one by one. So how to select the best x variable uh, from the given set of variables when you are splitting each node into two, right? So that is the first problem. And the second problem is when you are adding new variables again and again, you have to have some criteria about when to stop splitting, right? So when you are adding more and more variables, the decision tree would grow. So there would be new and new splits in the decision tree. And in the second problem, or the second key decision that you have to make is when to stop splitting more from the current node. Right? So when you come to a certain state of the decision tree, then you have to decide whether you should continue splitting uh, the tree and grow it more, or whether you should stop uh, adding new nodes and splitting. And that is the second problem or the second decision that you have to make during this cart algorithm. So let's see how to take how each of the decisions are taken by the cart algorithm. The first decision, which is selecting the x variable to get split, is basically taken on the basis of maximizing the purity of uh, classification of the selected node. What does this mean? So when you are adding a new variable or a new node, why are you adding a new node into the tree? You are adding a new node just because you want to reduce the impurity, right? Or you want to increase the purity of the tree, right? So when you are adding a new variable to the tree, that decision is based on, so that means which variable has to be added now has to be based on which variable would maximize the purity of the decision tree in the current state, right? So you have a decision tree like this. Something like this, right? So whether you should add the new what is the variable that you should have, you should add to this particular node, right? So you have a set of x variables remaining, right? So you have added some of the variables to the existing nodes, and you have several like x3, x4, something like that. These are remaining, right? So x6, those are remaining in the existing variable set, right? So you have to check which of these three should be added to this node. So you add the x variable to this tree, which should maximize the purity of the classification tree, right? So you can select either x3, x4, or x6, but you find, for example, you can select x4 because adding the x4 into this particular node would uh, maximize the purity. That means you would classify that particular node with much higher purity when you add this x4 variable into this particular node, right? That is how you take the split in decision. That is how you find the best variable to be added to the tree when you want to classify, right? When you want to build the tree, right? The second decision, which is about when to stop, right? Stopping criteria. So this stopping criteria is taken based on uh, these two uh, conditions, right? So mainly it can uh, reduce reduce the reduction of purity uh, added to the new nodes has to be considered, right? That means when you add a certain new variable into the decision tree, uh, you have to check how much purity reduction is that sorry, reduction of uh, sorry, this is about reduction of impurity, right? So it should be, sorry, this is something wrong, right? So this is impurity. How much impurity is reduced, or how much purity is added when you add a new node into the tree, right? So sometimes if it adds only a very small amount of purity, or reduce only a little bit of impurity, it may not worth adding a new variable, this particular new variable into the tree. So you may better stop adding new nodes and finalize your decision tree, right? If it is adding a huge amount of purity, then it may be worth adding the new variable into the tree, right? And when you are adding a new variable into the tree, uh, when you have to add the computational power or the memory complexity, that means how much memory that you have to allocate for these new nodes has to be increased as well, right? So when you're adding a new node, then your decision tree would get larger. So it would become much difficult. That means it would take much computation cycles to process this particular tree when it grows larger, and it would take a lot of memory uh, process this tree, right? So when you are adding a new variables, you have to think about how much compute, whether the addition of new node would create too much computation or uh, memory complexity. That means you are adding uh, much more memory. So this is not memory complexity, this is mainly just the memory itself, right? Into your uh, by adding a new node. When you are, if your reduction of impurity is very small, and it would increase the computational burden much more into this decision tree, then it would not be worth at adding a new node into this tree, right? If it would add a small amount of extra computation burden, but if it would reduce a lot of impurity by adding this particular variable, then it would be worth adding a new variable, adding this particular new variable into the decision tree, right? So that is the basis. Whether you are deciding whether you are going to add new variables or whether you are going to stop, right? Stop adding new nodes. First decision is based on which variable that you are going to add. The second decision is based on whether you should split more uh, of the when it comes to the decision tree. Right? So first look at the stopping criteria of the splitting. Right? Uh, when you are splitting a new node, that means once your existing decision tree, when you select a specific node, and when you are going to add a new node by splitting an existing leaf node, uh, you have to uh, consider several factors, right? So first thing is you have to consider whether that particular node that which we are considering is 100% pure at the moment, right? So that means if you, for example, if you have a decision tree like this, right? So now you are suppose you are considering this node, right? So if this node can classify your data with 100% accuracy, that means this node can uh, have 100% purity, then you don't have to add any more nodes, right? So that is obvious, right? So for example, uh, if this is the uh, variable known as the BMI greater than 80, right? So if after this variable, if for all the data points, if the data can be classified with 100% accuracy, that means all the data points can be classified with 100% accuracy after this node, so no errors, that means you don't have to add any more nodes into this particular node, right? So then you have to stop adding new nodes into this particular node. Maybe you have to consider other nodes later, but for this node, you don't have to add it, right? So this is the first condition. And the second condition is you, you may have a predefined maximum depth, right? So because of the computational requirements, that means you can't process a very large tree. You may have, you may want to have a certain fixed tree depth, and so this is also a requirement for the for a purpose of regularization as well. So we will discuss it later. So there may be a fixed predefined variable which is known as the maximum depth. So that means how much deep the tree is. For example, in this one, from here to here, 1, from here to here, 2, 1, 1. So this the depth of the tree would be 2, right? So you may have the maximum depth of the tree like, for example, 5. Right? So you can't have more and more nodes into this tree more than 5, and you have to stop by the by 5, right? So you can't have depth more than 5 because this would uh, create overfitting. So we may have already set up this hyperparameter or this particular uh, hard-coded value known as the maximum depth before we start this algorithm. So once this maximum depth is uh, fulfilled, then you can't add more nodes. So that is another stopping criteria. And also, you can have another predefined variable known as the uh, max impurity reduction, right? Threshold. That means you should have, you may have a, minimum impurity reduction, right? That means when you add a new node into a particular uh, node, there should be a impurity reduction, right? So as we explained, so you add the new node only when there is a impurity reduction or a purity addition. If there is if the impurity reduction is lesser than this predefined variable, that means adding uh, this particular node is not worth, right? So when you're adding a new node, it would increase the computational burden and the memory requirement for the machine. So it's not worth adding these new nodes when there's a uh, when the impure reduction is lower than the minimum predefined threshold, right? So this is also actually can be considered as a regularization related requirement, where when you can have this would also reduce the this would also try to reduce the tree size, so that there would be some regularization, and this would avoid the problems of overfitting, right? So in order to avoid the overfitting, we try to keep the tree uh, size smaller as possible without adding unnecessary nodes into the tree. So in this case, we are using this predefined variable, use this predefined threshold for minimum impurity reduction. So if this is not exceeded, you don't add a new node into the tree. This is the second stopping criteria. And when you find that when you come to a certain data point and you find that the number of data points, data in the current node is lesser than a predefined threshold. So this is another predefined threshold, is known as the uh, minimum number of data, right? That means suppose this data set would contain like 10,000 data points. For this particular tree node, you would have 5 data points. So it may be not worth uh, adding a new node to this particular node for just classifying 5 data points, right? Because within the 10,000 data points, when you start at here, all the other nodes should take care about the uh, 9,995 data points, and only this node is taking care of 5 data points. So adding more additional data point, adding more nodes for below this particular tree node may only try to classify, may try to uh, increase the accuracy or reduce the impurity only for a very small amount of data points. So it may not worth adding new tree nodes after this particular node if there are only 5 data points at that particular uh, tree node, and it is going to, even though it is, even adding more nodes would increase the purity, it's not worth adding more nodes because there are only 5 data points at this particular data point. So you can just stop splitting from this particular node, right? So now let's see how to add a new node. So the criteria of adding a new node into the decision tree, which is also known as splitting, right? So this is the first decision of the cart algorithm. So when you add a new variable, you add a new variable only when the new branching would reduce the impurity, right? So if there's no impurity reduction, you simply don't add any node, right? Uh, and when you add a new node, the impurity should be reduced. That means in the current node, for example, would have a certain level of, say, like so we would say how to measure the impurity in the future, right? So so the impurity is not at a certain level at a particular tree node. For example, in this tree node, there's a certain level of impurity. Once we add this, there are two variables, and then if the total impurity from these two nodes are lesser than the impurity at this particular node, then only we add this particular variable. That is when we add the new node, right? So when we add the new node, we select the variable which should reduce the impurity as much as possible, right? So you have certain x variables remaining, like x5, x6, x8, something like this. You select the best variable for this particular tree node, which should reduce the impurity as much as possible. So this is how we are selecting the categorical variable from the available set of variables. So in order to find how much impurity is reduced by adding this particular variable, you have to measure the impurity, right? So we say that impurity and impurity. So what is impurity? So how can we find whether uh, this classification would add more value into this to the outcome, right? So this is what we mean by impurity, right? For example, zero impurity or 100% purity means 100% purity or 0% impurity means our classification is 100% successful. That means for all the data points are classified with 100% accuracy in this particular tree node. So then we call it as 100% purity, right? So in this kind of scenarios, we don't add new nodes under that particular tree node, right? So in order to measure the impurity or the purity, there are several measurements. One is known as the Gini index, or Gini index, sometimes we pronounce, right? And the second one is known as the entropy. So these two are the commonly used measurements for impurity or purity, right? And variance, so we already know, is used for regression trees. In the CART algorithm, generally we are in the CART algorithm, you can use this decision trees for both classification and regression, right? When you are using the regression, you are using the CART algorithm for regression, you can use variance as the impurity when you are using the decision tree for regression purposes. But when it comes to classification purposes, these two are the measurements that we are using to calculate the impurity in a particular node. So impurities, for example, when you get 100, so when it comes to this particular decision tree in this particular node, if we have, so there are, say, like 300 data points in the root node, and in this node we have got, after classifying with this particular variable, you have two outcomes, right? In this first outcome, we get 200 data points you have classified to this category, and for this particular node you have got 100 data points. So after adding a certain variables, if the data can be classified into like 0 for example 50 for this type and 50 for this type, there's a certain level of accuracy that would be added uh, by adding this particular tree node, right? This particular categorical variable. So when you have data points like this, where we have the proportion of data points are 50 by 50, each of the classes, where each of the data point would not be having higher level of accuracy. Say like this one is only 50% accurate, and this particular value is also 50% accurate. So there's no accuracy added at all, right? So this one is, so this node has added 0% uh, impurity in for this particular scenario, right? So this is not the example, right? So this is not about dividing the 100 into 51 50, but if these 50 data points are relevant to 50% accuracy, and these 50% data points are relevant to 50% of accuracy, that means you have not added any uh, purity by adding this particular variable, right? So maybe you may not want to add this particular variable because it is not adding any accuracy, right? But say like with this 50% data point are 100% accurate, and this particular 50% data points are also 100% accurately classified. So then the purity of this purity added for by adding this particular categorical variable is 100%, right? So you can it's better to add this variable so that it would classify its 100 data points 100% accurately, right? So it may be a good decision to add this uh, variable if these 100% data points are classified 100% correct. So this accuracy is calculated by using this Gini index using this formula, right? So 1 minus I1 to C is the number of classes, right? So in this case, if it is a binary classification problem, the y is 2, right? Uh, and pi is the data proportion of ith class, right? So if there are two classes, uh, so this is the total number of data in the node, and this data proportion means total number of data in the node in the which is dividing the number of data in the ith class of the node. For example, in this case, if there are 50 data points in this class, and total number of data in the tree node is 100, right? So this one would be 50 by for the first class, for this class 50 divided by total number of data nodes are 100. It would be 0.5, right? Sorry, this is 0.5. Similarly, you can calculate the impurity based on the proportion of this particular class in the for all the data points given, right? So when it comes to, so how do you intuitively understand this Gini impurity, right? For example, when your data set can be classified like 0% for uh, into classes like 0% and 100%, then it may be 100% accurate, right? So there is a high so this Gini index is actually, it's what, so intuitive what you have to understand is it is evaluating the amount of discrimination that happens in each of the class, right? Based on the frequency. That means if they are dividing by 50 by 50, they are not discriminating, maybe not discriminating too much, right? If it is discriminated like 90 and 90 for one node and 10 for one class, so then it would be classifying more, right? That means with much discrimination, right? So this discrimination is measured by this Gini index. Actually, this Gini index is not, or the Gini index is not only used in this scenario, but in economics, this Gini index is used for measuring the income distribution of a country or wealth distribution of a country, right? So the same Gini index is used here to find how much distribution is uh, not pure, right? The similar kind of measure is known as measured uh, by entropy, which is uh, which is giving a similar kind of impurity, but with a different kind of mindset, right? So the entropy is also the way in physics where how it is measuring the purity, right? Or the randomness or the chaos in a system. So when we measure the uh, entropy, we measure uh, it, it with this formula where you can see it starts with the negative sign. That means it's always negative, right? So when there's no disorder or when it is 100% pure, that means when your classes are 100% purely classified, then this entropy denoted by H becomes 0, right? So when there's some impurity only, it should have some value which should be a negative value, right? So this one is also calculated in the same way where C is the number of Y classes from 1 to C, and now it is the value is pi log 2 to the second base uh, pi, right? Pi is the proportion of for the ith class divided by the total number of data in the particular node. So this is a similar measure to the Gini index to measure the impurity, but those are used either one of them in most of the cases. Uh, in this case, you can see it's the formula is much easier to calculate because there are only square you have to calculate. But in this case, you have to calculate the log value, so it would be a bit computationally expensive to calculate the entropy, right? So sometimes instead of entropy, you can use the Gini index because of its computational simplicity. But sometimes entropy is used, but in practically none of them are too much better than other one. In the when it comes to empirical studies, they have found uh, not none of them are significantly better in performance when used. So in most of the cases, some people are using Gini index because they are computationally simple, right? So when you map the uh, value, that means the disorder or the impurity level, right? Uh, Impurity value with the proportion. This is how the Gini and the entropy are distributed, right? So when the proportion is 0, that means 0 and 1, there's no disorder or there's no impurity, right? So because the classes are 100% classified. When it is 1 also, that means when one class is 1, that means the other class is 0, right? So other classes are 0. So then also it is 100% pure. when they are in middle, that means the proportions are like 0.5, then there would be the highest level of impurity, right? For the entropy, the highest level of impurity is 1, right? For the Gini impurity, the highest point of impurity is actually 0.5. So you can mathematically prove by using the above formulas. For the entropy, the maximum value of impurity is 1, and for the Gini index, it's 0.5. But when you are using it in the machine learning algorithms, both of them are empirically giving similar kind of performance when it comes to the accuracy of the model, right? Okay, now let's look at the classification geometry. That means when you represent the classification problem, which we study in the mathematical way, how these data points are classified in the Cartesian coordinates, how this classification happens in a decision tree. Right? So in this case, I have selected age as the x1 variable and BMI as the x2 variable. Right? You can see these are the people that would be having cardiovascular diseases, the red color ones, and the blue color data points are relevant to healthy people. Right? So maybe you can use these two variables, where the age is greater than, so you can, because this is age is a continuous variable, we take 35 as the uh, point where we are classifying whether it is greater than 35 or lesser than 35. And for the BMI also, we select the value 80 as whether this particular person is higher than 80 or lesser than 80, so that you can use another decision boundary. Right? So from 35 you have this decision boundary, and from 80 of BMI you have this decision boundary. So by using two decision boundaries, you can have uh, with first with this decision boundary you can have this area, right? With this decision boundary greater than 80, you have this decision boundary. So when these two areas are combined, you can have this particular area where the two x1 and x2 variables are satisfied, right? So here you can find the uh, people with cardiovascular disease, right? So now here you can see that both of the decision boundaries are parallel to the axis, right? So this decision boundary is parallel to this axis, right? This decision boundary is parallel to this axis, right? This means in the decision trees, your decision boundaries are always parallel to the these are actually linear hyperplanes when it comes to multidimensional vector spaces. So these linear hyperplanes are perpendicular to their axis, right? So now let's think why this was like that, right? In the when it comes to linear regression and logistic regression, uh, you have different decision boundaries. Like when it comes to linear regression, also, or even with classifications, you have decision boundaries like this, right, or this. But when it comes to decision trees, you have only you have this linear decision boundaries, but they should be uh, parallel to the axis, right? x-axis, x1 axis, x2 axis, and so on. So being parallel is actually a limitation. Limitation means you can't have decision tilted decision boundaries like this, which can be easily used for classifying the data points, right? So this may seem like a big disadvantage in decision trees, right? But the problem is when you want to have these tilted lines, you have to maintain extra parameters, right? So you have to maintain the uh, gradient information in the decision boundary. Right? For each of the uh, lines, you have to maintain the gradient parameter. So when you are maintaining these values, so then it would be an extra parameter in the model. That means when you are having extra variables, extra parameters in the model, that is a that causes a disadvantage, which is when you are having too many parameters, we know, right? So we would be having the curse of dimensionality. So adding more variables is a disadvantage when it comes to tilted lines, tilted decision boundaries. So, so the scientists have tried to find these kind of decision boundaries for uh, decision trees as well, but what they have found was that uh, so whether you should have these kind of tilted decision boundaries with extra parameters, or whether you should have these kind of existing decision linear hyperplanes that are per perpendicular or parallel to the other axis with a lesser number of parameters. So what they have found was both of the approaches perform the same, right? That means both of the types of decision trees uh, would work similar. That means their performance would be similar, but when it comes to the simple form where you don't have any tilted lines, tilted decision boundaries, your computation would be much faster because the computation requirement is low, so that you can uh, process or calculate numbers faster when it comes to the simple approach where you are using parallel decision boundaries to uh, axis. Right? So that is why we are not using these tilted decision boundaries these days uh, for decision trees. Not because we can't, but because we don't need, because we can, instead of using tilted decision boundaries, you can use uh, uh, multiple parallel decision boundaries with many number of variables, and you can increase the accuracy of the decision boundary uh, without moving into tilted decision boundaries, right? Like in linear regression or logistic regression, right? So that is why what makes the model, this decision tree model, simpler and faster, so that you can use it in much advanced versions known as ensemble model. So we will be discussing it now. Right? So before that, let's see what we have to do when the x variables are continuous. Right? So even in this current example, we have used age, which is a continuous variable, right? The BMI, body mass index, which is also a continuous variable. So how did we convert this continuous variable BMI into a categorical variable, which is BMI greater than 80, right? How did we do that? So when you are when you are using these kind of continuous variables, when you are using them in decision trees, you have to convert them into categorical variable, right? Categorical variables. So you have to learn how to convert these continuous variables into categorical variables so that it can be used in decision trees, right? The first thing what you do when you are converting a continuous variable to categorical variable is you consider all the possible splits using all the data points as split points. Okay, so what does this mean? That means, say this is the BMI, right? Body mass index variable, which is a continuous variable, but your data set has only some of the values, right? This value, maybe this value, this value. There are only some values, right? One would be 80, 85, 100, 105, right? This is maybe 65, 60, and so on. Suppose these are the uh, values that we have in our data set, right? What we do is we take each of the uh, data point and we try to classify, right? Uh, when you take this one, there are no values before lower than 60, so we don't take this one. So we take this one and we find that there's only one value before this one and there are several values after this point, and we find using the y variable, we find how much uh, entropy or the Gini index is there when you are classifying this BMI by 65, right? So you can calculate for each of the data point what is the, for each of the, by taking each of the data point as the uh, pivot point or the point where you are uh, making this categorical variable as the pivot. You can see, for example, you can take 80 and we can find these values as one class and these values as another class, right? You can use 85 also, and you can use these values 80 and 65 and 60 as one class, and 100 and 105 as another class, right? So by taking for each of the data points, you can also find what is the uh, impurity in the y variable, right, for all the data points, right? So then we can find the data point which is having the, or the splitting point which is having the least entropy, right? So you take all the data points of the data set and then you try to split the data set. uh, you try to create the categorical variable by splitting use on this particular value, right? For example, we try to divide by 65 and we take the values lesser than 65 as one class and values greater than 65 as another class, and then we measure the entropy, and then we take the value 80 and then we 80 as the splitting point and we measure the entropy, and so on and so forth. We do it for all the data points, and then we take the uh, value which is given the least entropy when used as the splitting point, right? So in this case, 80 is the value where you have got with the least entropy, right? So that means when you get a continuous variable, you split the continuous variable by the point which is having the least amount of entropy, right? And then once you have selected this particular splitting point, then you encode all the data values. That means all the data values in the data set are given in continuous variable. So instead of having continuous values like 6, 65, and so on, you can have, in this case, binary values for each of these data points, right? For example, for this value, we can have 0 because they are lesser than this particular value, right? So other values are 80, 85, 100, 105 are put as 1 for the positive case, right? So this is how we can convert this continuous variable into a categorical variable so that they can be used in the decision trees, right? Okay, now we know how to make a decision tree, right? Actually, how to build a decision tree as well, right? So now we can apply the knowledge we have about the bias and variance into decision trees. So unlike the other some other algorithms like linear regression and logistic regression, when it comes to decision trees, you can add actually many number of variables, right? So for example, say you have 50 x variables. By adding these 50 all the 50 uh, categorical variables into a single decision tree, there's a high chance that you have a decision tree that can make the predictions 100% accurately, right? But remember that this 100% accuracy is achieved only in the training set, right? So you are building a decision tree so that it is classifying the data much accurately by adding nodes more and more to optimize the training set, right? So when you are having like 100% accuracy, that doesn't mean your machine learning model is 100% accurate or it is perfect, right? Whether it is a perfect model, it is not, right? So because 100% accuracy can be achieved, it would be achieved by having a significantly large number of variables in a significantly large decision tree, but that doesn't mean this model is 100% accurate because this 100% accuracy is only for measured only for the training set. When it comes to real world data like the test set, the decision tree would perform worse, right? So this is a problem with high variance, right? So when you have a very large decision tree with large number of variables, you can make a low bias. That means your accuracy would be much high, but this is only for the training set. So it is a high variance or overfitting uh, decision tree, right? So this decision tree can also be considered as a low bias and but high variance machine learning algorithm, right? So this depending on the way that we make the decision tree, right? So uh, as I mentioned earlier, if you have some regularization related parameters like maximum tree depth, or the minimum amount of entropy that should be increased uh, by adding a new node. So those kind of parameters you can set so that your model is not going to overfit, right? Unless that, so if you are just adding more and more nodes just to increase the accuracy or reduce the impurity, so you would get a highly overfitting model if you are using this decision tree algorithm, right? But however, you can increase the regularization as I explained and will explain now, right? And make smaller decision trees. that have lower variance, right? So by having large number of x variables, we can have a very large decision tree with high variance, but with regularization techniques, you can make smaller decision trees. You without going to with all the x variables, by only using some of the x variables, you can have smaller decision trees with low variance but high bias, of course, right? So when you are not using all the variables and not trying to optimize more and more, your model may be high in bias, but it would be lower in variance. So advantages, then you can have uh, many number of different decision trees for the same data set, right? So we will see what we can do with those many number of decision trees in future, right? So before that, let's see how to do the decision tree regularization, right? In the earlier cases we have just simply explained, but in here we are going to explain more about the decision tree regularization. Uh, say you have a minimum limit of data points, right? That means per node. That means uh, if your node is having a few number of data points, that means you are not going to split it more, as I explained earlier. So that means you are not uh, going to add more and more nodes to classify smaller number of data points. So that is that is one of the regularization technique. And you can have maximum tree depth, just as I explained. So this would avoid having larger uh, trees, which would be having much overfitting, right? And you can have, in order to limit the size of the tree, you can have maximum number of nodes in a tree, so that would limit the size of the tree, right? And you can have uh, minimum decrease in loss. That means you can introduce the uh, minimum amount of impurity reduction to add a new node, right? And there's another technique known as the tree pruning. So we will not be explained in detail. So that is about once you have created the decision tree, then you can remove some of the nodes so that the impurity reduction where you remove some trees, sorry, where you remove some nodes that are not that much significant, which should reduce the tree size significantly. And that is known as tree pruning, where you have a larger tree and then you can reduce the tree into a smaller tree, like cutting the uh, edges of the tree, right? So in a physical real world tree, biological tree, you cut and prune them. You can cut an existing large tree, decision tree, and make it a smaller tree. So using the validation data set, right? And once we have do this kind of regularization, and then we come up with uh, many number of decision trees that are smaller in size, but when we find many number of decision trees with less overfitting decision trees, and then we can combine them together and make a single model known as ensemble model, right? So when it comes to ensemble models, so ensemble models are models that can have many number of the same machine learning algorithm and have much higher level of performance, right? So when it comes to ensemble models, decision trees are generally used because decision trees are computationally cheap compared to cheaper compared to other machine learning models, right? So the idea of ensemble models is mainly about having the concept of wisdom of crowd, right? So for example, when it comes to selecting the ruler of a country, instead of selecting a specific person to appoint the uh, ruler of a country or president of the country, we use the vote of the all all population, right? So that means instead of finding a single person's opinion, by having many people's opinion and getting their vote, we can get, the idea is that we will get a much higher accuracy in its decision, right? So there are some drawbacks in this decision, right? As you may already know, but when it comes to independent decision making, if the people are not get fed with similar kind of information with bias, the people can make decisions, and when they vote together, their vote would be highly accurate than any of the individual person's opinion, right? That is the idea of ensemble methods. So you have small, many number of machine learning models, and they are working together, and then their full ensemble model is performing better than any of the individual machine learning model, right? So in this case, we are using decision tree ensemble methods in this lesson mainly, and there are several types of there are different types of ensemble methods known as bagging, boosting, and stacking, right? So for stacking, we are using for heterogeneous, combining heterogeneous machine learning algorithms, which we are not going to cover here, right? So let's see what is for before looking at bagging uh, this one. So we would be looking at bootstrapping, right? Bootstrapping is a resampling technique, right? That means when you suppose you have a limited data set and you want to train many number of decision trees. That means in order to make the uh, ensemble method, you want to train many number of decision trees, but you have a limited number of data points. So using the same data set is not good, because there would be some statistical reasons where when you are using the same data set, there would be some overfitting that would possible. So what you do is, instead of using the same data set, you can create multiple data sets by using the technique known as bootstrapping, where you get the data set or you get the original data set or the training data set, and make another set of data sets by sampling with replacement. So with replacement means you once you get, for example, if you have like 100 data points in your sample training data set, and you want to make uh, 50 data point samples out of this 100. So what you do is you randomly select 50 data points from this sample, right? So once you get a sample data point, you put that you take it into this data set, and then you put that value back into the original data set, and then you sample again for the second data point, and then you put that value back into the data, to the original data set, and sample again, and so on so forth. You take 50 samples from the original data set, not by simply taking these data points and keeping with them, but at the same thing again into the original data set. So this is known as uh, the technique known as sampling with replacement, right? With this technique, the same data point may be replicated in the, for example, certain data point may may appear only once in this particular data set, but it may happen 2 or 3 times or any number of times in the sample data set, right? But when you get similar data sets, several such similar data sets from the original data set, this data set, and this data set, we have 3 data sets in this case. So you can train 3 different decision trees with these data sets, with these sample data sets, and that is known as the technique called as bootstrapping. So this is an example for bootstrapping, where you have, suppose these are the data points, right? For the first data set, you get a woman, this large woman, and put her back into the data set, and get another data point, which is this big girl, right? and you get this uh, girl again, this girl for the first time, and then you get this big girl again, right? So this big girl is uh, occurs only once in this original data set, but in this sample data set, this big girl occurs in 2 times, right? Here and here, right? Because each time we get the sample value, we put it back into the original data set, and then you continue sampling, right? You can see this black man appears 2 times in this data set, the sample bootstrap data set sample, because we put them back, right? So then in here also you take another samples with replacement, where you can find this man appears 2 times in this data set, but here only one such black man appears in this or in the original data set, right? So you, in this way, you can have many number of bootstrap data sets, and each of these data sets can be used for training a different uh, machine learning model, in this case a decision tree, and we can make a ensemble model, right? So now let's come to the topic of bagging. The bagging stands for bootstrapping and aggregating, right? B for bootstrapping and AGG for aggregating, right? So in this case, what we do is we uh, do the bagging, uh, and then we get the aggregated value, right? Where we are getting the average value from each of the predictions, right? When it comes to regression problem, and when it comes to classification problems, we can get the use the voting to get the final outcome, right? So you, for different data sets, for sample data sets, you have different machine learning models. When it comes to classification problem, all the votes, all the machine learning models are voting for the outcome, and if this one votes for 1 and this one is also voting for 1 and this one is voting for 0, final vote would be, vote result would be 1, because 2 are voting for 1 and 1 is voting for 0, right? So this is how the voting works, and each of the machine learning model is voting for the in the bagging technique. In the random forest is also bagging technique, but the difference is, instead of using the whole variable set, so suppose you have x variables available, right? So number of x variables are available for each of these smaller models, each of these decision tree models. uh, we don't take all the x variables available in the original problem, right? So generally we select only a subset of x variables for each of these machine learning models, each of these decision trees. Generally, the number of x variables selected are the square root of total number of x variables, right? This is just some uh, uh, rule of thumb value, but you can select any number of any proportion of the x variables from the available x variables. Uh, this algorithm is significantly better. That means have a lesser variance compared to uh, a single decision tree. The advantages, so this advantage comes with almost no increase in bias, right? So when it comes to bias variance trade-off, we say that when we try to reduce the variance, the bias is increased. But when you are using this kind of random forest kind of technique, you can actually uh, reduce the variance by almost no increase in bias, right? So the another advantage of random forest is you can use non-scale data when it comes to other learning techniques. With gradient descent, you have to do scaling with the standardization and normalization. But when it comes to random forest, you can easily use the data without any scaling, so that it works really fast, right? You don't have to do these kind of pre-processing or scaling when you're applying the random forest, right? And also, this random forest can also be used for feature selection uh, as a feature selection technique, which although we haven't discussed it in detail, right? So this is how we do. We have different type of different training data sets, and we tra train different decision trees with each of the data sets, and then we do the voting or averaging when it comes to regression, and then we can get the final prediction. Boosting is also a similar kind of regularization technique, which is a similar kind of ensemble method, but instead of having uh, so in the case of boosting, what we do is we can have similarly we can have low bias ensemble method uh, with but instead of using the exact bagging technique where you are using where you taking the samples uh, by simply bootstrapping in parallel. We take the samples, or we make the models one after the other, so that it is increasing the accuracy. That is the change difference between bagging and boosting, right? So what we do is once we uh, train the models uh, in the bagging, we train the models, all the models simultaneous, right? We can do it in parallel where we are making the uh, data sets using the bootstrapping uh, in parallel, and then you can train the models in parallel. But in boosting, uh, we get the sample and train a model, and then after, based on the results of that particular model, we get another sample, and then we train another model, and then we get the accuracy and get using the results of the model, then we train another model, and so on, right? So we do the model training and sampling one after the other in the boosting, so that the accuracy is increased, right? So this may be much higher in variance or overfitting, because we are trying to fit to the data set in each of the step. But this is in general, these boosting techniques are much accurate compared to bagging techniques, right? So in today's world, we are when it comes to practical application of decision trees, the boosting techniques are widely used. So some of them are ADA boost, gradient boosting machines known as GBM, and there are versions of GBM known as light GBM and extra gradient boost or XGBoost, right? So in this case, just look at how the XGBoost works, uh, which is one of the currently used, widely used technique, right? So in XGBoost, the bootstrapping is used, and these each of the decision trees generated sequentially, where once the uh, once this particular once a single decision tree is trained, and then you find which data points the decision tree is failing, right? And when you are sampling for the next decision tree, you take higher proportion of data from the missing values or the failed values in the original decision tree, right? That is how we train the XGBoost, and this is much more accurate in compared to random forest. So this is how it is done, where for example you do it sequentially, where you get the original data set. So suppose this is the data set, and then we do the classification with the with the model, and you find for these particular data points the model works correctly, and for these particular data points, the model was not accurate. So when you are taking the sample, now you can see now there are the proportion of green data points are reduced, which were working correctly, and for these data points, the proportion of these data points are higher in the second data set, second data sample, right? So and with this data set, another model is trained, and then we find the data points which were working fine. So now you find these data points were accurate. For these data points, it was not accurate. So now we have added higher proportion of this data set for creating the new sample, and now you can find there are green data points as well in the new data sample, and then you create another model, and then you classify the data set, and then you find this data set, and then you do it again and again until a certain stopping criteria, and you can use all of these. You can get the what or average of all these classifiers to get the final outcome in the XGBoost, right? So this XGBoost is much accurate compared to when you tune it correctly with the hyperparameters. You can do you can get very high level of performance in using decision trees, right? So the advantage of decision trees is that they are very fast at learning, right? So because and they can run in parallel as well in some of the cases, uh, and you don't have to uh, tune the hyperparameters too much like in decision trees, like in neural networks, right? Uh, and also when you are using decision trees, smaller decision trees, you can use then for interpreting the data, right? So when you are saying that you have a higher proportion in uh, you can classify the cardiovascular diseases with the BMI very accurately, that means there's a high probability that the BMI is affecting the health of the person, right? So this kind of interpretation can be done when you are using decision trees with smaller sizes, right? And it can also be used for feature selections, which we have not discussed here. And so the disadvantage of decision trees is that they are not that deep. That means they can't have much higher level of info. Uh, they can't learn deeper level uh, features like in neural networks, where neural networks can have like in some neural networks you can have hundreds of layers in the neural networks, but decision trees don't have that much of layers or depth, so they can't learn that much. So for very complex learning for requirements like natural language processing, decision trees may not be using cannot be using with the current technology. So that is another disadvantage in decision trees, and also transfer learning kind of techniques where you can transfer the existing knowledge from one decision tree to another decision tree is not that much used in these days compared to neural networks, where in neural networks you can train it for a certain data set and use that same information in another neural network with for much accuracy. But so that is another disadvantage in decision trees. Right. So this is all for today. So if you have any questions, just ask.